Welcome everyone to today's lecture on potentiometry, a key technique in pharmaceutical analysis. This method allows us to determine the concentration of a solute in a solution by measuring the potential difference between two electrodes. I will be guiding you through the principal, equipment, and application of potentiometry. Here is an overview of what we will cover today. We will start with the basic principle of potentiometry, then move on to discussing different types of electrodes, including reference and indicator electrodes, as well as glass electrode. Each of these plays a crucial role in the potentiometric analysis. Potentiometry is a branch of electroanalytical chemistry focused on measuring potential without any current flow. The core setup involves an electrochemical cell with two solutions connected by a salt bridge, as you can see in the diagram, and electrodes. This setup allows us to measure potential created by the movement of ions between the electrodes. Electrochemistry is a part of chemistry which determines electrochemical properties of substance. An electric current is required for measuring current, which is the unit is ampere, denoted by A, and potential also voltage, which has a unit of volt, V, created by movement of charged particles. Now the galvanic cell, that is the electrochemical cell, this is in the figure 1, this figure here as you can see, serves as an example of such system. Three distinct charge transfer processes are described for the system in figure 1. Electrons move in electrodes and wires from zinc electrode to copper electrode. Ions move in solution. In the solution on the left, zinc ions move away from the electrode and sulfate ions move towards it. In solution on the right, copper ions move towards the electrode and negatively charged ions, that is the sulfates, away from it. In the salt bridge, positive ions move right and negative ions move left. On the surface of electrodes, electron transferred to ions or vice versa. Like for instance, zinc electrode dissolves. Metallic copper is decomposed on the electrode surface. Potentiometry, we measure the concentration of solutes by determining the potential difference between two electrodes when there is no current flow. This method is highly sensitive and it's used to gauge the concentration of an analyte in various solutions. Potential is the tendency of an electrode to lose or gain electrons. This concept is central to understanding how potentiometric measurements work, as the potential difference between electrodes reflects the concentration of ions in the solution. The standard electrode potential, that is E0, is the potential of metal electrode when it is placed in 1 molar solution of its own ions at a temperature of 225 degrees Celsius. This value is used as a reference point to compare the reactivity of different metals. The standard potential can help predict whether a metal will be oxidized or reduced when it comes into contact with another substance. Oxidation potential refers to the tendency of substance to lose electrons and thereby get oxidized. It is the potential required to remove electrons from an atom or ion in electrochemical terms. A higher oxidation potential indicates a greater tendency for the substance to lose electrons and undergo oxidation. Reduction potential is the opposite of oxidation potential. It measures the tendency of a substance to gain electrons and thereby get reduced. A higher reduction potential indicates a greater likelihood that the substance will accept electrons and undergo reduction. In electrochemical cells, substances with high reduction potential are often the ions that get reduced. Potentiometer. Potentiometer is an instrument which can measure the potential developed without drawing any current. In simple form, it consists of two electrical circuits in combination. Measured potential can be used to determine the quantity of analyte in terms of solution. The principle behind potentiometry is that when a pair of electrodes is placed in a solution, the potential difference changes as the concentration of ions changes. This is often observed during titration, where the potential shifts as the analytes react with the titrant. The two indicators used are the reference electrode, which maintains a constant potential, the indicator electrodes, which indicates the potential change. The solution must be stirred during titration. And during titration, the active ingredient being determined produces an electric potential with a suitable indicator electrode. The titration is followed by the fall in potential as the ingredient is used up by the titrant. Or the titrant may cause production of potential at the end point when titrant is no longer being used up by the active ingredient. The sudden increase in the titrant concentration results in sudden increase of potential. The endpoint is determined by sudden change in potential. From the endpoint determination, the concentration of active ingredients can be measured. It is irregular titration, but instead of the indicator, we use the potentiometer. It measures the changes in potential and can be used in all kinds of titration like the acid-base titration, redox titration, complexiometry, and so on. Now, based on potential measurement of electrochemical cells without any, as I said, without any appreciable current, the use of electrode to measure the voltage from chemical reactions. These are the few principles. A potentiometric cell consists of a reference electrode, an indicator electrode, and a salt bridge. The potential of the entire cell can be represented by the sum of the potentials of these components, as shown by the equation here. The E cell equals to E indicator plus E reference plus E junction. The E reference is a half cell having a known potential that remains constant at constant temperature and independent of the composition of the analyte, e.g. like calomel electrode and the silver chloride electrode. An indicator electrode has a potential that varies with variation in the concentration of an analyte. Most indicator electrodes used in potentiometry are selective in their responses. Metallic indicator electrode and membrane electrodes are the types of indicator electrodes. The third component of potentiometric cell is the salt bridge. The salt bridge is used to prevent interference of the analyte solution with the reference solution. Analyte solution is a sample solution whose potential is to be measured. Analyte. Now, the indicator electrode is the electrode which responds to the change in the potential of the analyte solution. The electromotive force, EMF, of the complete cell, that is the E, you see E cell, is given by the following equation. E cell, as I said, equals to E reference plus E indicator and plus E junction. E meaning the electromotive force of reference, the electromotive force of indicator electrode, the electromotive force of and the unit of the potential are mile volts, denoted by MV. a potential developed across the liquid junctions at each end of the salt bridge. The junction potential across the salt bridge is, that is the EG. EJ is small enough, is very small enough to be neglected. The reference electrode, such as the standard hydrogen electrode SHE and the silver chloride electrode, have a known and stable potential. They are crucial for providing a stable point of comparison in potentiometric solution. In potentiometric measurement. The reference electrode is the electrode which consists of its own potential value, and it is stable when dipped in the sample solution. The indicator electrode has an unknown potential. It is immersed in the analyte solution. The potential is directly proportional to the ion concentration. As I explained earlier, the electromotive force of a complete electrochemical cell is the total voltage generated by the cell. This voltage is the sum of the potential contributed by the various components of the cell. E reference, this is represents the electromotive force of the indicator electrode. E indicator. The E indicator, E reference is stable and unknown. Is known. Used as the baseline to measure the potential of the indicator electrode. The indicator electrode is unknown. The potential is unknown and is directly proportional to the concentration. The indicator electrode is the one where the reaction of interest takes place, and its potential changes depending on the concentration of the species involved in the reaction. The salt bridge salt bridge, that is EG, as I said in the previous equation. This term accounts for the electromotive force at the salt bridge, which connects the two half cells of the electrochemical cell. The salt bridge minimizes the liquid junction potential, that is the voltage difference that can occur when two different solutions come into contact, and completes the circuit. So now the E reference has a constant value. The indicator electrode varies based on the reaction. The salt bridge is typically small and can be negligible, but is included for accuracy. This equation is fundamental in potentiometry and other electrochemical techniques, where the goal is to measure the EMF to gain insight into the concentration of ions in the solution or the progress of a chemical reaction. A salt bridge. A salt bridge is a crucial component, even though its value is negligible, but it is added for accuracy, and accuracy matters. A salt bridge is a crucial component in an electrochemical cell, serving several important functions to ensure proper function of the cell. Now, the functions of a salt bridge, when you say it maintains electrical neutrality, what we mean is, during the redox reaction in the electrochemical cell, one half cell may accumulate positive ions, that is the cation ions, while the other accumulate negative ions, that is the anion ions. This imbalance in charge can stop the reaction by creating an electric potential that opposes further electron flow. The salt bridge allows the migration of ions to maintain electrical neutrality in each half cell, enable the redox reaction to continue. When we say again it prevents solution mixing, we mean that you see, when there is the direct mixing of the solution from two half cells could lead to unwanted side reaction that can interfere with the primary reaction of interest. The salt bridge physically separates the solutions while still allowing ionic conduction, thus preventing these side reactions. When we say it reduces liquid junction potential, when two different solutions come into contact, a small voltage difference known as the liquid junction potential can develop due to differences in ion mobility. The salt bridge helps to minimize this potential by providing a pathway with ions that have similar mobility, thus ensuring electromotive force. Now, when we say, how does this salt bridge works? Now, pay attention. It's not in the note. Please pay attention. You see, in an electrochemical cell, oxidation occurs in one half cell, producing electrons and positive ions. The electrons flow through the external circuit to the other half cell, where reduction occurs. The positive ions in the oxidation half cell migrate towards the salt bridge, while the negative ions from the salt bridge migrate into the reduction half cell. This ion exchange through the salt bridge keeps both solutions electrically neutral and prevents charge buildup that could halt the reaction. The common salt bridge electrolyte. The electrolyte used in salt bridge is usually a salt that does not react with other chemicals in the cell. For instance, like the potassium chloride is a common choice because the potassium and chloride have similar mobility, which helps in reducing the liquid junction potential. Potassium nitrate as well is another common electrolyte used in salt bridge. Now, the importance of this salt bridge in electrochemical cell. Now, without the salt bridge, the chemical cell would quickly reach a point where the reaction could no longer proceed due to charge imbalance. The salt bridge thus plays a vital role in sustaining the flow of electrons and the overall function of the cell. The salt bridge ensures that the electrochemical cell functions properly by maintaining charge balance, preventing solution mixing, minimizing liquid junction potential. So it's as much as the value can be negligible, it is very, very important in electrochemical cell. Looking at this diagram, as you can see, this is the solution. From the lectures, you can easily detect the salt bridge, the electrode, the reference electrode, the indicator electrode from this. The theory described relates to the fundamental principle of potentiometry, which involves measuring the potential of an electrochemical cell to determine the concentration of an analyte in a solution. The core of this theory is the Nash equation, which is used to relate the potential of an electrochemical cell to the concentration of ions involved in the reaction. The Nash equation, which is E equals to E naught, as you can see in the equation here, E equals to E naught plus, in bracket, 2.303 RT over NF log 10Q. Here is the breakdown of each term in this equation. Please pay attention. I'm going to explain some things here. E, electrode potential of the solution. Now, this is the actual potential measured by the electrode when it is immersed in the sample solution. It is dependent on the concentration of the ions in the solution and the condition of the system. E naught, which means the standard electrode potential. This is the potential of the electrode when it is in the standard state, meaning it is in a solution where the ion concentration are 1 molar and the temperature is 25 degrees Celsius or 298 Kelvin. The standard electrode potential is a known value for specific electrodes and serves as a reference point. R is the gas constant, which is 8.314 joule per mole Kelvin. This is a physical constant that relates energy scale to temperature, and it is used in many equations in chemistry and physics. T, as you know, is the temperature and is measured in Kelvin. The temperature affects the movement of ions in solution, and therefore the potential is measured. Therefore, the potential is measured. Therefore, the potential and it affects the movement of ions and also the potential measured. The number of ions, N meaning the number of ions transferred, in a redox reaction occurring at the electrode, N is the number of electrons that are transferred per molecule in the reaction. This is a key factor in determining the potential, while F is the Faraday constant, which is 96,500 coulombs per mole. This constant represents the charge of 1 mole of electrons. It is used to convert between the energy of the electrons and the voltage in the equation. Reaction coefficient, that is Q, is the ratio of the concentration of the product to the reactant in the electrochemical reaction at a given moment. It indicates the direction in which the reaction is proceeding. For a general reaction, now understanding this Nast equation in potentiometry, the Nast equation shows that the potential measured by an electrode is not only dependent on the standard electrode potential, but also on temperature, number of electrons involved in the reaction, the concentration of electron of the reactants, and the products in the solution. That is represented by Q, that is reaction coefficient. In potentiometry, we use the Nast equation to relate the potential measured by the electrodes to the concentration of the ions in the solution by knowing the standard electrode potential and measuring E. We can determine the unknown concentration of ions in the solution, often referred to as the analyte. Now, there are some key points. The logarithmic relationship. The equation indicates a logarithmic term, indicating that the relationship between the potential and the concentration is logarithmic. This means that small changes in concentration can lead to significant change in potential. Temperature dependence. The equation shows that temperature plays a vital role in determining the potential, as higher temperature can increase the kinetic energy of the particle, thus affecting the potential. Well, in summary, the Nast equation is the central to potentiometry because it allows us to calculate the potential of an electrochemical cell based on the concentration of ions in the solution and other factors. Now, by measuring this potential, we can infer the solution, the concentration of an analyte, which is the main objective of potentiometric analysis. I hope you understand this. These are mainly used to measure voltage. Mainly 2 electrodes are used in potentiometry. They are as follows. I said the reference electrode or the standard electrode, or the indicator electrode, which is the test or sample electrode. The reference electrode, such as the standard hydrogen electrode, that is the SHE, and the silver chloride electrode have a known and stable potential. They are crucial for providing a stable point of comparison in potentiometric measurement. The standard hydrogen electrode is the primary reference electrode. It consists of platinum foil, which is coated with platinum black and immersed in HCl solution, which contains the hydrogen ions. Hydrogen gas is passed over the platinum foil through the side tube. This is used for the entire pH range. The disadvantage of this electrode are the instability due to the presence of oxidizing and reducing agents and the purity of the hydrogen. The standard hydrogen electrode SHE is the reference electrode used in electrochemical measurement to provide a stable and reproducible reference potential. Its construction involves several key components and steps to ensure its accuracy and reliability. Now, here is a detail of the description of its component. We have the platinum electrode. The platinum, it's made of a platinum wire or foil, is used as the base electrode. The platinum is chosen for its inertness and stability in electrochemical reaction. The platinum surface is often coated or treated to ensure it is clean and has a high surface area. It may be covered with a thin layer of platinum black, a finely divided form of platinum. That is a platinum black. Now, to enhance its catalytic activity, there is this hydrogen gas supply. The electrode is equipped with a gas inlet that allows hydrogen gas to flow over the platinum surface. The hydrogen gas used should be of high purity. It is often supplied from a gas cylinder and needs to be free from impurities that might affect the electrode performance. There is this acid solution. The electrolyte. The electrode is immersed in a standard solution of strong acid, typically 1 molar hydrochloric acid, to ensure a constant concentration of hydrogen ions. The acid concentration now. The concentration of the acid is crucial as it determines the pH of the solution and the activity of the hydrogen ions. The hydrogen gas needs to diffuse effectively over the platinum surface. The design often includes a mechanism to ensure uniform gas distribution and minimize bubbles or turbulence that could affect the measurement. Now, during construction, the platinum electrode and the acid solution are housed in a suitable electrode body, often made from materials like glass or plastic that are resistant to chemical attack. The assembly must be sealed properly to prevent leakage of the acid or the hydrogen gas and to ensure stable operation. The standard condition for SHE, that is the standard hydrogen electrode, are at 25 degrees Celsius. The electrode is calibrated and operated under this condition to ensure consistency. Hydrogen gas is supplied at a pressure of 1 atmospheric pressure to maintain standard condition. The electrochemical cell occurring at the standard hydrogen electrode is as follows. Half hydrogen atom giving rise to this equation, this half cell equation. The reaction is at equilibrium and the potential of the SHE is defined as 0.00 volt as standard condition. To measure the potential, in use the SHE provide a reference point reference potential of 0.00 volt against which the potential of the other electrode, that is the working electrode, are measured. The potential of the SHE remains constant as it is defined as the standard reference electrode, as I said earlier. In summary, the construction and the working of the SHE. The SHE is constructed using a platinum electrode, a high purity high purity hydrogen gas supply, and a standard acid solution. It operates under well-defined standard condition and provides a stable reference potential of 0.00 volt for electrochemical measurement. The construction ensures the electrode stability and reproducibility, making it a crucial tool for determining electrode potential and calibrating other electrodes. The saturated calomel electrode is a common reference electrode made from mercury and mercury-1 chloride immersed in a saturated solution of potassium chloride. Its potential remains constant, making it ideal for use in potentiometric analysis. It consists of porous disc at the base of the electrode, which is clogged. Above it, the glass tube is filled with potassium chloride crystal, and above it, it is filled with the calomel paste, which is prepared by grinding of mercury chloride with pure mercury and milliliter of the saturated potassium chloride solution. Then pure mercury is placed in the electrode vessel. The advantages are the easy to construct and are highly stable. Explanation: this is how the calomel electrode looks like. The silver chloride electrode is another electrode composed of silver wire coated with silver chloride and immersed in a solution saturated with potassium chloride. It's commonly used in potentiometric measurement due to its reliable potential, same as the saturated calomel electrode, where the silver wire is coated with the silver chloride solution. Here the wire is dipped in the saturated potassium chloride solution. The cell consists of the following: silver chloride, and potassium and chloride with the half equation, as you can see in the diagram and the reaction here. Let me point it out. As you can see here and here. And this is how the silver chloride electrode look like. Indicator and reference electrode are both crucial components in electrochemical measurement, but they serve distinct roles in the process. Here is a detailed comparison. When you talk about function, the indicator electrode, the purpose is that it measures the potential of the analyte in the solution relative to the reference electrode. The potential measured is indicative of the concentration of the specific ions or the pH of the solution. Like for example, a pH glass electrode for measuring pH, ion selective electrode designed for specific ions like sodium, potassium, or chloride. The reference electrode purpose It provides a stable and constant reference potential against which the potential of the electrode is measured. It maintains a fixed potential that is unaffected by the composition of the solution being tested. For example, the saturated calomel electrode or the silver chloride electrode. When we talk about construction, in the construction of the indicator electrode, typically consists of sensing elements that interact directly with the analyte. For instance, a glass electrode has a glass membrane that is sensitive to hydrogen ions, that is the pH, while an ion selective electrode contains a membrane selective to a particular ions. The material used is specific to the type of measurement. For pH measurement, it's usually made of selective special glass. For ion selective electrode, it may be a polymer or crystalline materials selective for the ion of interest. While for the reference electrode, in the concentration, it contains a stable reference system, usually with a known and constant composition. For example, now, a calomel electrode has mercury and mercurious chloride, and a silver chloride electrode has a silver wire coated with silver chloride. And the materials used are chosen from for their ability to maintain a stable potential. This often includes elements like silver mercury or calomel. Calomel is mercurious chloride. The role in measurement. Well, the indicator electrode detects change in the analyte solute concentration or the pH by responding to the electrochemical potential at the surface of the electrode. The potential change is used to determine the concentration of the analyte. The response of the indicator is specific to the ions or pH of the solution it is measuring. While in reference electrode, it provides a constant reference potential to which the potential of the indicator electrode is compared. This stable reference allows for accurate measurement of the potential difference. The potential of the reference electrode maintains stable and does not change with the solution composition. When we talk about stability and maintenance, it is its performance for the indicator electrode. The performance can be affected by factors such as contamination, aging, and changes in the solution. Regular calibration and maintenance are required. There is need to be clean. They need to be clean, calibrated, sometimes replaced depending on usage and wear. While the reference electrode the design is to provide just a stable reference and the potential over time, reference potential over time, and it's less affected by the sample solution, and it requires less frequent maintenance but needs to be kept in proper storage to maintain stability. The uses in electrochemical cell. Indicator is used as the working electrode in the electrochemical cell, which interacts with the analyte to generate a measurable potential, while the reference electrode is used as junction with the indicator electrode to complete the electrochemical cell. It provides a constant reference potential to measure the potential difference accurately. In summary, the indicator electrode measures the potential related to the analyte and provides that on the concentration or activity of the species of interest, while the reference electrode provides a stable and known reference potential against which the potential of the indicator electrode is measured. ensuring accurate and constant measurement. From the explanation, I hope you understand potentiometry.